NASA engineers are testing machines in a simulated Mars environment in California right now that look nothing like any rover humanity has ever sent to another planet. And the reason they abandoned the traditional design reveals what the next generation of Mars exploration is actually being built to find. At NASA's Jet Propulsion Laboratory in Pasadena, California, there is a facility called the Mars Yard, a carefully constructed outdoor testing ground filled with rocks, slopes, sand traps, and terrain features, engineered to replicate the surface conditions of Mars as accurately as possible on Earth. This is where every Mars rover NASA has ever flown was tested, refined, and broken repeatedly before its flight version ever left the planet. And what is being tested there now represents the most significant rethinking of planetary exploration robotics since wheels first touched Martian soil. The current generation of Mars rovers, Curiosity, which landed in 2012, and Perseverance, which landed in February 2021, are extraordinary machines. Perseverance is roughly the size of a car, weighs approximately 1,025 kilograms, and carries the most sophisticated scientific instrument package ever delivered to another planet's surface. It has been actively collecting rock core samples in Jezero Crater, an ancient lakebed that scientists believe held liquid water billions of years ago, sealing those samples in titanium tubes for eventual return to Earth. Its performance has been remarkable, but its limitations have also become instructive. Wheeled rovers, for all their reliability, are fundamentally constrained by terrain. Curiosity's aluminum wheels have sustained visible damage from sharp Martian rocks over its years of operation. Steep crater walls, deep sand, cave systems, and the rugged terrain where some of the most scientifically interesting targets exist remain effectively inaccessible to wheeled vehicles. The places most likely to preserve evidence of ancient Martian life, or shelter any hypothetical present-day microbial survivors, are precisely the places wheels cannot go. This is where NASA's prototype testing has taken a radical turn. One of the most striking systems developed and tested at JPL is EELS, the Exobiology Extant Life Surveyor, a snake-like robot composed of multiple articulated segments with rotating propulsion units, designed to navigate terrain no wheeled or legged vehicle can attempt. EELS was tested extensively at JPL facilities, on ski slopes, and in other challenging environments, demonstrating the ability to traverse loose ground, climb through confined channels, and adapt its entire body shape to the terrain it encounters. While EELS was initially conceived with icy moon exploration in mind, the locomotion technology it validated feeds directly into the design thinking for future Mars mission architectures, particularly for exploring Martian lava tubes, cave systems, and subsurface voids that orbital imaging has confirmed exist. The aerial dimension of Mars exploration is advancing simultaneously. The Ingenuity helicopter, the small technology demonstrator that traveled to Mars attached to Perseverance, was originally designed to attempt just 5 flights. It completed 72 flights over nearly 3 years before sustaining rotor damage in January 2024, shattering every expectation and proving definitively that powered flight in Mars's ultra-thin atmosphere is not just possible, but operationally valuable. Building on that legacy, NASA has unveiled the concept design for the Mars Chopper, a significantly larger rotorcraft with 6 rotor systems, capable of carrying science payloads of up to several kilograms across distances of up to 3 kilometers per Martian day. Where Ingenuity was a proof of concept the size of a tissue box, Mars Chopper is designed as a genuine science platform, able to survey terrain, access cliff faces and crater walls, and scout locations no ground vehicle could reach. The testing philosophy driving all of this development reflects a hard-earned lesson from decades of Mars exploration. Every system destined for Mars must survive conditions that are brutally unforgiving. Temperature swings from 20 degrees Celsius down to negative 90 degrees Celsius in a single sol, dust storms that can envelop the entire planet, radiation exposure without the protection of a magnetic field, and communication delays of up to 22 minutes each way that make real-time control from Earth impossible. Prototypes at JPL are deliberately pushed to failure in simulated conditions, redesigned and pushed again, because on Mars there are no repairs, no rescues, and no second chances. The autonomy software being tested alongside the hardware may ultimately matter even more than the machines themselves. Perseverance already uses AutoNav, a self-driving system that allows it to navigate Martian terrain and plan its own routes around obstacles significantly faster than earlier rovers that required step-by-step commands from Earth. Next-generation systems and testing extend this autonomy further, enabling future rovers and rotorcraft to make scientific decisions independently, identifying promising rock formations, prioritizing targets, and conducting preliminary analysis without waiting for instructions from a planet hundreds of millions of kilometers away. All of this technology development converges on a single strategic goal: preparing for the missions that will definitively answer whether Mars ever hosted life, and laying the robotic groundwork for eventual human arrival. The samples Perseverance has cached are awaiting a retrieval architecture. The subsurface environments where biosignatures are most likely preserved are awaiting machines capable of reaching them. And the human missions NASA envisions for the 2030s and beyond will depend on robotic scouts that have already mapped the terrain, tested the resources, and identified the hazards. The machines being broken and rebuilt in a rock yard in Pasadena right now are the direct ancestors of whatever finally answers the biggest question humanity has ever asked about Mars. So here is the question I want you to answer in the comments. If next-generation robots could finally access the Martian caves and subsurface environments, where evidence of life is most likely preserved, do you think we find proof of ancient Martian life within the next 20 years? Or does Mars keep its secrets, even from machines built specifically to uncover them? Follow this page right now if you want to track every step of humanity's search for life on Mars, because the technology being tested today becomes the discovery headlines of tomorrow, and we cover it all every single week.